Okay, so this slide is kind of a repeat from what we saw earlier regarding the preliminary system safety assessment. Realize again, this kind of starts to occur during the preliminary design phase. So in this case, we really try to establish safety requirements regarding the system and item. So what systems and items of the aircraft function? Sorry. So basically, one thing we're going to start talking about is reliability. So before we can do that, let's refresh a couple of concepts from probability theory. If you have a probability density function, like in this particular case, it's a normal distribution or Gaussian distribution with zero mean. You see, you know that the probability that the x, which is on the x-axis, is larger or equal than a certain value x, is really, a certain value capital X, is really just the integral from capital X to infinity over the density. And of course, this integral, you can just interpret that as being the area underneath the curve from this point, which is capital X, all the way to infinity. Yeah? So it's the area underneath this probability density function, PDF. So I did the same thing for a Rayleigh distribution as well. Same thing happens. Now let's replace the probability density function by a failure density function. Then in the failure density function, we can now determine concepts of reliability. Yeah. So what you see here, you see on the vertical axis, you see the failure density. On the x-axis, you see the time. So for example, if you want to specify the probability of a failure within time t, for example 2, then that's going to be given by the integral underneath this curve from 0 to 2. For example, 2 being hours, 2 hours. So it means that this q is the unreliability. That's the probability that the system is going to fail within t hours. In other words, in this example that I show here, t equals 2. Then the reliability is 1 minus that. So it's 1 minus q, which is of course the remaining area, which is this green area underneath this curve. In other words, is the integral from t to infinity, or in this example, 2 to infinity. So the failure density is the curve, the area underneath is given by, on one end, unreliability, and the other one, to reliability, and you know that the reliability is 1 minus the unreliability, and the reason is that the area underneath the failure density function should be equal to 1. Now, so this also means that if the unreliability is given by the integral of this function f, that means that f is given by the derivative of q as a function of t. Now, if we know that q as a function of t is 1 minus r as a function of t, and if you take the derivative towards t of this is going to be derivative of 1, which is 0, and derivative of minus rt, which is minus derivative of r dt. Well, why did I put this there? We go back to this in a little bit. So let's now officially give a definition for reliability. It's really defined as the probability that a product or system will be operational for a specified period of time given a specified environment. So it implies statistical properties. And we saw this on the previous example. If you say, the reliability, this particular reliability in this example, this area underneath the curve represented the probability of survival beyond time t. What's my probability that I actually are working longer than 2 hours in this case? I'm surviving beyond 2 hours. That is what this reliability is all about. Now let's relate the reliability to the failure rate. If you look at the failure rate and you look at it kind of generally speaking, that the failure rate lambda t is the number of failures per unit time divided by the number of components that are exposed to the failure. Yeah? So if we define the number of failures per unit of time as dnf dt, change in the number of failures in a time interval dt, how many how does the number of failures change over time? Of course, this will increase. And then on the other end, we define an S as the number of survivors. So you see, the longer you wait, of course, more systems will fail, and this number of survivors will actually decrease, whereas the number of failed units will increase. So if you look at that, and we look at this lambda, that's really going to give us the number of failures per unit time, dnf/dt, divided by the number of components exposed to failure. And of course, that number that's exposed to failure is equal to the number of survivors. Then also we know that the total number is equal to the survivors plus the failed numbers. So if you do that, you can actually rewrite this lambda as, we can actually take this equation, pre-multiply by n naught over n naught, which is of course 1. Then we just move these two around. Then you see that this total number divided by survivors gives you actually the number, the 1 over reliability. Tells you that how many survivors are there after a certain amount of time over the total number of items. Tells you a little bit, okay, what's the probability that you're going to survive past a particular period of time. And on the other side, if you look at this is of course just going to be the failure density. So lambda t is really the failure density divided by the reliability, if you think about it. Now, if you look at that, and you take into account that ft was given by minus dr dt, now what you see is lambda t will become a differential equation as a function of r. Yeah? Lambda t dt is equal to minus 1 over r dr dt. You integrate both sides, and you get that reliability is really the exponential of the negative integral from 0 to t of the failure rate. Yeah? Now, for a lot of cases, the failure rate is assumed to be constant. So if it's assumed to be constant, this integral from 0 to t of lambda as a function of t dt, lambda as a function of t becomes just lambda, the constant lambda. So then this integral becomes minus lambda t. So it means that during this portion, or useful life, where we assume a constant failure rate, that reliability is given by a negative exponential, e to the minus lambda t. On a typical lambda curve, you see there's two, this is not always constant. Early on, there's actually an increased failure rate because that's often referred to as the burn-in period. We actually tried, there's a lot of initial errors. And of course, after things wear out after a while, the failure rate will increase as well. But during a useful life, for which we design the system, typically lambda as constant is a good assumption. Okay, so far let's recap. If we assume that the failure rate is constant, equal to lambda, r will be e to the minus lambda t, ft will be lambda e minus lambda t, and qt is 1 minus e to the minus lambda t. Now, well, if you work out the Taylor series expansion of this, then for small values of lambda t, that would be equal to about lambda times t. And think about it this way. The unreliability, the probability of failure in a time interval t, is of course basically approximated by the number of failures per unit of time times time. Yeah? So that would be your easy way of looking at it. So typically, as a rule of thumb for lambda times t is smaller than 0.1, this approximation is valid. Now, as a result of time, of course, it's a negative exponential. So if you plot that out, you know that after a certain amount of time, and in this case, my failure rate is 10 to minus 3 per flight hour. It always starts out working, probability of 1, and of course, the probability of survival will just exponentially decrease as a function of time. Another thing that's often used a lot when evaluating systems is what we call the mean time to failure. So in a sense, the mean time to failure is just really kind of the expected value of t given the failure density function. And of course, this is really just equal to taking the integral from 0 to infinity of the reliability. So if you just assume again, like we did on previous slides, that lambda is constant, you just take the integral from 0 to infinity of e to the minus lambda t, and that will give you 1 over the failure rate. So an approximation, so the mean time to failure is really 1 over the failure rate. There's also other failure rate models, and in this slide and next slide I just mentioned another one, which is the Weibull failure rate. We're not going to talk too much about this. Alright, let's look at a couple of small examples. Assume that we have a failure condition that can occur during the flap activation, which happens an average of 6 minutes per flight hour. This failure condition has a failure rate of lambda is 10 to the minus 4 per flight hour. Now I ask you, what's the probability of this failure condition for 1 hour of flight? So what you have to realize, that reliability is the probability that something fails during exposure time. So if we have a lambda of 10 to the minus 4 per 60 minutes, but you have to realize the exposure time in this particular case is at 6 minutes. That's the only time interval that we're using the flaps. Okay? So that means that exposure time is 6 minutes times the failure rate. You get a probability of 10 to the minus 5. And of course, we're assuming that the probability of failure is lambda times t, so we have to always cross-check after we get the result if this is truly smaller than 0.1. And of course, in this particular example, it is much smaller than 0.1. So we find out the probability of failure is, I made a mistake here, that's not the reliability, it's 1 minus the reliability, of course, or 1 minus e to the minus lambda t. So make sure to, I'll update that in the slides. So this is another example that you can look into and just wonder. Alright, so let's another distribution that we'll see, and we'll get back to this later, is the Poisson distribution, and that's really the probability that there's going to be X failures in a particular interval from 0 to t. Okay? So without actually giving any proof, I showed that this probability of X failures is equal to lambda times t to the power x times e to the power minus lambda t divided by the factorial of x. For example, if x would be equal to 1, this would turn into lambda times t to the power 1 times e to the power minus lambda t. Yeah? If there's 0 failures in that interval, this will become lambda t to the power 0, which is 1, divided by 0 factorial is 1. So that is e to the minus lambda t, which is actually the reliability. Okay, now another thing, we talked about mean time to failure, and we said earlier that's typically expressed as 1 over lambda. But if you want to look at maintainability, for example, we want to kind of find out how much time there is on average between failures. And of course, the mean time between failures is equal to the mean time to failure plus the mean downtime. And the mean downtime can be determined by a variety of factors. How long it takes to repair it, maybe some administrative issues. But if you only attribute it to repair, you could approximate the mean downtime by the mean time to repair. And this mean time to repair, just like the mean time to fail, is related to another parameter, which we can define, which is the repair rate, which is the opposite of the failure rate. So similar to MTTF being equal to 1 over lambda, MTTR could be equal to 1 over mu. So this means that MTBF is equal to 1 over lambda plus 1 over mu is lambda plus mu over lambda times mu. Alright, so the next item is the fault tree analysis, and we'll talk about that in the next video.